I'm Katie.
I'm Vinny, and this is Learn Real Good.
Yeah, it's a podcast. A podcast about what, Vinny?
It's a podcast about science that tries not to take itself too seriously.
Like us.
We don't take ourselves seriously at all.
It's about 99% goofy times with us.
And
1% serious. Like tax season.
Yeah, as serious as a tax audit.
Even then, we usually make some jokes.
Yeah.
Not on the form. CRA, if you're listening.
CRA
we take
is
the
scouring
forms.
podcasts for people confessing to tax fraud.
I'm so scared. Well, you know me. I'm a good girl. I like to abide rules. I love knowing the rules.
Yes.
I ask a lot of questions about the boundaries of the rules in any sort of scenario. When it comes to taxes, I take it very seriously. I'm so scared of accidentally making a mistake.
You're very diligent.
But it's scary.
I guess so.
It seems easy to make a mistake on those forms.
Yeah, I mean, they're very confusing.
They're not obvious.
They're not intuitive. They're not made for people to be like, oh, just do your taxes. Here you go. Push a button.
Yeah.
They're made to be rigorous, detailed, and overly labyrinthine.
Labyrinthine. Wow.
Yeah.
I like it. It makes me think of labyrinth.
Yeah, I think that's the adjective for the noun.
You think it's related?
Maybe.
Labyrinth and labyrinth. I thought it had nothing to do with one another. That is some wild stuff.
Well, one of the things we like to do at the beginning of the show is share a fun fact with each other.
Yes.
Now, who's going to go first
Oh
today?
my. I think you went first last time.
Sure, then why don't you go ahead?
All right. Vinny.
Yes, Katie.
We are talking about bees.
Yeah, we are now.
Okay, so I'm sure you've heard. Well, let's see if I can pop quiz you, Vinny.
Okay, pop quiz hot shot.
Okay, so you know that bees aren't doing so hot. Do you know the name of this sort of phenomenon?
Colony collapse disorder.
Wow, amazing. And how would you describe what that is?
The colony doesn't do well to the point where it, some would say it collapses.
Right.
As in a systematic way is to be termed a disorder.
So that's a very diplomatic answer. So it is, the colony sort of falls apart and dies, but it's not just everything just drops dead.
Okay.
There are things that can cause a colony for everyone to die, like acute poisoning from a pesticide.
Sure.
But colony collapse disorder is a very particular phenomenon where the worker class seems to die off or abandon the colony while there's still lots of food in the queen, so they get left behind. That's what a
proletariat revolt.
Maybe. It's all politics.
Right.
So do you know, what would you say is the main cause? Do you know what's causing colony collapse?
It's just wealth inequality.
Yes.
The bees are way more class conscious than the rest of the animals.
Seriously.
No, I have no
idea.
clue. No.
Okay. Well, there's many proposed causes, but one of them is varroa mites.
Varroa mites.
So varroa mites are a type of mite, which is like related to a tick, like an arachnid type organism that will
just point into your head.
I know this is not a video podcast because the one picture I have from this article shows the varroa mite on the bee's head, so I feel like I need to show the
You reenacted the picture.
Yes,
from
I'm reenacting the picture.
Okay.
That's how I normally convey information from a picture.
Naturally.
Yeah. Okay, so these mites are causing the disease, the bees to die. That's one of the causes. Now, these bees, so as you might think, if we want to protect the honeybees, because they're important pollinators,
get rid of the mites.
Get rid of the mites. Here we go.
We solved it.
Here we go. So how do you do that? So they're close relatives of insects. So if you try to treat them with a pesticide, you're going to kill the bees who are sensitive. No offense, bees, but you are.
I'm very emotional.
So how do you target the mites? So there's a fungus that will kill the mite and not kill the bee. That has been sort of proposed as a potential treatment, but there's a catch.
There's always a catch.
There's always a catch. So the fungus doesn't do well at really hot temperatures.
Okay.
Like the temperature in a hive. So beehives are usually like 35 degrees Celsius.
Oh.
The fungus naturally would die under that temperature. So how do you do that? So this art, we're finally getting to it. You know, I like a lot of backstory.
I love
it's
the
like
setup.
me telling any story. The fact is a second. The backup 10 minutes. 3 hours later. So
in conclusion.
So this article came out June 4th of 2021. And the scientists did some sort of selective evolution of the fungus to select for certain traits, such as being able to survive and thrive at warmer temperatures so that they can be used to treat the varroa mites and protect the honeybees from this one cause of death.
Wow.
They also selected for other traits, but I thought I would leave it at that.
Yeah,
pretty cool, eh?
That is very cool.
Yeah. So what they did, actually, this is sort of neat too, is they sort of treat it with hydrogen peroxide, which causes a lot of mutations. So they just sort of prime it to have a bunch of random mutations, right? And then they stick it in a hot room, and whoever survives happens to have the mutation that allows it to survive. You take them into the next generation. They were able to increase the rate of spore production by the fungus from like 40% to like 70% in like 7 generations. So it's not amazing. That seems so easy.
Why didn't we solve this sooner?
Well, we haven't been working on it, but we'll give these scientists some feedback.
Yeah, we have a lot of notes for them. Well, that's cool. That's a great. Right? That's a really nice natural way of hopefully helping out these colonies.
Well, yeah, because pesticides will always, they often will harm things you don't want it to, right? They're not selective and they stay in the soil for a long time, whereas these biological alternatives have a shorter half-life and can be better targeted.
And we all know those things never have unintended consequences too, so that's great.
You say that because I studied invasive species, and so many species have been introduced for that purpose, and it always, often backfires.
Now, are you ready for my fun fact?
I'm never ready, but let's do it anyway.
You can skip it.
No, I'm excited, but if you pop quiz me, I know I'll do terribly.
No. Okay. So here's one. Rechargeable batteries. This is a question.
Wow.
What is an element that is used often in rechargeable batteries?
Oh, I think I know where you're going.
Do you? Yeah.
It's lithium.
Yeah.
Yeah, I think I read this.
You've read this?
I heard something about making lithium batteries last longer.
No.
Damn it.
That's all. Yeah, that's research is always ongoing.
I thought I read something about
lithium. But this one is. I thought this was really fascinating. So lithium usually is mined. It's like a relatively abundant material, but you got to like dig it out of the ground. Wow. Mining is really bad for any kind of environment. However, lithium is present in very large quantities in the oceans. At low concentrations, but because there's just so much ocean, there's quite a bit of lithium.
So it's like dissolved in the water, just floating around in the water?
Water has so much stuff in it. There's like gold and everything in there, all at very, very low concentrations. But
is it naturally occurring, or is that a byproduct?
No, it's just a naturally occurring. There's like, it's one of these like low proton elements. They're just everywhere.
Lithium might be listening.
You low proton element. It's a real diss for all the elements. Yeah.
Ooh, okay.
Let's not talk about hydrogen. Am I right?
Was it number? Oh gosh, never mind.
I think it's 3.
I was gonna say 3.
Yeah.
I was like, you know what? It's better
been a
than
while
not
since I said, but I think it's 3. In any case, there's so much in the ocean. Is like, it'd be great if we could extract it from there. Oh. And so these scientists came up with a membrane that it will filter out anything larger than lithium, but it will let lithium through if you apply a voltage to it. And so you just stick this giant, like, it's like a ceramic membrane that goes in the ocean. You apply, or you just take ocean water, I guess. You apply the membrane and you can filter out the lithium. You have to keep pumping all of this through. Now, it's not super efficient. You have to apply a bunch of electricity to get a bit of lithium, but what's great about it, what makes it feasible to actually use this, is that part of the process is that at one end of the cathode, the positively charged, nice. You get hydrogen gas, which is, you can sell that, and then at the other end, I think you get like chlorine gas, which you can sell at the other end.
Okay.
And then part of the byproduct, once you filtered out so much of this stuff, the water is considered desalinated, and now it's fresh water.
Whoa.
So your byproduct are hydrogen gas, which you can sell, chlorine gas, which you can sell, and then you end up with fresh water, which is always useful. And there's so much desalination going on that you can actually look at a desalination plant, take the desalination plant's wastewater, and that's already done a whole bunch of work for you.
Okay.
And so there's like a symbiotic relationship. So you can either take ocean water, look for the lithium, and sell the fresh water, or make fresh water and then take the byproduct of that and look for lithium. And so because there's all these knock-on side effects by this process, they think it's like an economically viable method of extracting lithium from the ocean.
And potentially could make desalination more economically feasible, right? If you have these other things that you could be selling off to offset the costs, because that's been a big holdup.
Use every part of the ocean. That's what I always say.
Interesting. So can you picture like people are going to invest in these membranes? It's like the new Bitcoin. We all buy a membrane. We go to the ocean.
We have to mine our own lithium?
From the ocean. Easy. We're not digging up ore. That's not practical.
But a lithium membrane to the ocean.
It's like panning for gold. Everyone's going to be panning for lithium.
What? Maybe you're right. Maybe that's our future.
Maybe
panning for lithium.
That's the most confidence you've ever had in my ideas. Maybe
is as far as I'll go.
Interesting. I remember seeing lithium in the news. Maybe I just read lithium. I'm like, they probably made the batteries last longer. Next, because I don't really.
That's usually where we think about it.
I'm not really interested in. I don't naturally gravitate towards those headlines.
Well, we did it. We shared fun science facts.
And now we get to the real fun bit.
Yeah, this is why we're here. So each episode we have a guest, often STEM grad students. They're going to talk about their research, and I'm really excited about our guest today. Yeah, today's guest is Tessa Krause. She's currently working towards her Master's of Applied Science at Queen's University. In her research, she uses a laser to measure how well another laser is melting metal. When she's not in the lab, she loves to teach her dog new tricks, find new spots to go hiking, and use her knowledge of the scientific method to bake the perfect sourdough. Hi, Tessa. Come join us.
Hi, guys.
Hey, Tessa. Thanks for coming on our podcast.
Thanks for having me.
Oh, it's a delight. The honor is ours.
For sure.
Lasers.
Metals.
This is much more up Vinny's alley in terms of knowledge.
Because I have the physics background, you have the biology background.
That's right. So I will get us started. Tessa, what's a laser?
So it's funny you ask that because my research actually doesn't really deal that much with how the lasers work. I took a course in my last year of undergrad, and light rattles around in a cavity, and the light that comes out has a lot of intensity in the same direction. I fortunately don't need to do the math for that anymore.
So what's the utility of sort of forcing light into this concentrated beam? Like, we use it for all sorts of things, but why is that more useful than a dilute light?
So if you have a flashlight or a laser pointer, and you point the flashlight at a wall really far away, you're probably not going to see the light anymore. But if you have a laser, even if you're like across a gymnasium from someone, they're still going to see that little dot on the wall. So you just have really concentrated light that's really predictable. So that's the advantage.
Predictability. So then if something changes, you can see that something's changed, right? Because you know where it's supposed to be?
Yeah, you know how it should be behaving.
Bad laser.
Yeah, we don't want misbehaving light.
No.
Very cool. Wow.
Yeah, so Tessa, why don't you tell us a little bit about using lasers to measure how well another laser is melting metal?
Yes, so I do mostly laser welding. You've probably interacted with something in the last week, whether it was a car. A lot of those components are laser welded now. Golf clubs, they're starting to laser weld, stuff like that. There's problems, though, where laser welding gives a lot of advantages compared to traditional methods, but it's really unstable. And it's actually funny your fact was about lithium today, because the main motivation for my research is lithium ion battery manufacturing. So we really worry about if you go too deep into the lithium, because if you hit the lithium with a big, powerful laser, your whole plant is going to catch on fire.
It's generally frowned upon.
No one likes that.
Why is that? Why is it so flammable?
Lithium's really thermally sensitive, so it doesn't like being exposed to heat. And what's scary about lithium ion batteries is they actually have everything they need inside them to burn without oxygen.
Now, are these batteries in my phone that I put next to my skull all the time?
Do you remember the Galaxy Note crisis a few years ago?
Oh, right, they were exploding. That's lithium?
That's lithium ion.
Nice.
Yeah.
We have to take a break for our sponsor, Galaxy.
We still love you, Galaxy.
Sorry, Samsung. But it's a very common problem in lithium ion batteries, like laptops, all sorts of batteries have that problem.
Then why are we using it?
because it's the best, unfortunately.
Yeah.
Damn.
Yeah. There's nothing else that works as well.
A lot of people in my research ask, oh, why don't we use a better battery chemistry? But that sounds like a chemistry problem, and I'm
Right.
Okay, so you're looking at how can we use lasers to make lithium batteries while dealing with this constant issue that deep lasers will explode the battery.
Yeah, so we use a second laser that's not as powerful as the melting one, and it takes pictures of the weld while it's happening, so we can figure out exactly how deep it's going. And we're taking measurements on the order of microseconds, which is a lot of bits of a second. And that gives us really good control over the process.
What made you get interested in laser technology, Tessa?
So I kind of had a bit of a weird career progression. When I was in high school, I was on the robotics team. I was one of the founding members, so that was very cool. And then when I got to university, I kind of wanted to keep doing stuff like that. So I ended up doing the Formula racing team because I figured a car is really just a gas-powered robot.
True.
And then from there, I ended up in high-tech manufacturing for an internship, and I became really interested in problems that we have with moving towards a greener future as we move away from combustion engines. And now I'm doing my master's.
Amazing.
Wow, very cool.
Yeah, and like when in your lab, do you have like a bunch of like lithium-ion batteries to practice your welding on?
So we don't. The university would probably kill me if I was welding lithium ion in the basement of the physics building with lecture theaters above me.
Right.
One lithium ion cell has about the same energy inside of it as a hand grenade. So that would be a little bit problematic. So my supervisor just buys me copper samples.
Interesting. So you're using copper to sort of as a stand-in for lithium. How can you know from, I guess, is this sort of how strong the laser is in terms of how deep it will go in copper translatable to other elements? Like how can you use copper as a stand-in for another element?
So in a perfect world, my laser will never touch the lithium. I only deal with the cases. So the cases are usually made of aluminum or copper.
Right.
Okay, so then it doesn't matter. You can stick chocolate in there. It doesn't matter.
Yeah, because laser welding is often used in chocolate bar manufacturing.
Wait for it, okay? Yeah. Cheese stuffed aluminum cases.
I'm waiting for this, yes.
And you melt the cheese. When you're done your research at the end of the day, pop it open over some Tostitos. You got yourself lunch. I'm just saying, it's a free idea. You're melting it anyway.
Yeah. Laser heated queso.
She's not sold on it. I think it could work.
This is actually a conversation I've had with my lab mates on a number of occasions about whether we could just move our 1 kilowatt laser over a piece of meat fast enough if we could cook it.
Right.
And of course, on YouTube, someone's tried it. And it turns out the laser actually ionizes the meat and it makes it taste really bad.
Yeah, that would be bad.
So it's a bad idea. If anyone ever buys you a $200,000 laser, don't try and cook meat with it.
And I bet it only hits the surface of it.
It would be like blue rare.
Yeah.
That reminds me of the time I tried to cook I tried to simulate s'mores by cooking a marshmallow over a Coleman stove.
Yeah, the propane gas is not tasty.
That was the closest to eating poison, pure poison. At least that's what it tasted like. You could tell this wasn't going well.
No, that's a bad idea.
I'm glad to be here. So is your whole lab like laser focused on lasers?
So we're a pretty small lab group. One half does fundamental research. They're doing single photon stuff, which is a little bit out of my depth. I'm more of an engineer. The other side, we have one person who does laser welding, except they're doing it for 3D printing. So they're 3D printing with metal, which has really cool applications for making custom hip replacements.
Whoa.
So how do you use a laser? Because in my head, a laser is used for melting or at least, melting stuff, I guess. And then how do you 3D print with melted materials?
Yeah, well, kind of. So what you do is you scrape powder over your surface, and then you only weld the regions you want to stick to themselves, and then you move your stage down, put another layer of powder, and weld again.
Fascinating.
Oh, so instead of pouring the material, you're zapping the material.
Exactly.
That's
Nice.
neat.
That is cool.
Oh man, 20 years from now it's going to be wild, hey?
Yeah, we're going to have 3D laser welders in our home.
Between CRISPR and 3D printing, there's some wild stuff coming
Someone's going to combine both
pipe.
of those.
I hope not.
We hope not, but probably. And so what kind, like, I guess, what is the question that you're asking? Like, how well does this work? What are the dangers? Like, how precise can you get it?
Yeah, so what I'm trying to do is I'm trying to improve an existing commercial system to go faster with how many measurements we can take. Because with the electric mobility sector, copper's a weird metal and you have to weld it really fast. And the faster you go, the less measurements you get, which means the less certain you can be the weld is good. So we're working on coming up with low cost ways to increase signal in problem regions.
And do you have to, I guess, like, how fast do you need to be is the question.
We go at 200 kilohertz and we can go up to 300 kilohertz. So
that's your measurement rate.
100,000 samples a second.
Wow. That's a lot.
So what's like the typical day for you right now in the lab, Tessa? You're just like, you press a button and it goes a certain speed and you turn some knobs and you press it again to see how fast it is. What does like a day in the lab look like for you?
A little bit. I was actually joking about this when I got home today. This morning I was in the lab. I got in at 9:30. I misaligned a mirror. And then I spent the next 8 hours trying to realign it.
Oh my gosh.
But I did get it realigned. And then I got to melt metal with lasers. But a lot of my day is aligning optics because the light beam is really small. So you have to put the small beam through a small hole.
And do you work on an optical table?
Yes, I do.
Yay, optical tables are neat. Now, Katie, do you know what an optical table is?
I haven't the slightest clue what an optical... I assume all tables are optical in that I can see them. Is that not what an optical table is?
No, it's not.
Yeah, nuts.
Tessa, why don't you give us an explanation of what an optical table is, please?
So it's a table that's really heavy because you don't want any movement with your optics because you're really sensitive to any bending or anything like that. And it has hundreds and hundreds of holes on it that are an inch apart from every other hole. Like it's a grid of holes. So then you can put your optics wherever you want. It's kind of like grown-up Lego, but with high power lasers.
What are the holes for? Like you screw things into it?
That's exactly it. They're all threaded. And you put mirrors in and your instrument and then a series of mirrors and you can split your laser and merge your lasers and put your sample in the right spot, and it's all made to be optically stable so that, you know, if there's an earthquake even, like, it might not affect it.
I mean, take a break. Are you physicists? If there's an earthquake, by all means, hide under your optical tables.
Nothing stops us.
The air conditioner is my nemesis right now with the optical tables, because every time our air conditioner kicks on, it blows air on my mounts and it makes them move by about a nanometer. And I can see that. So.
Oh, man. Do you have like an easy way of knowing that something has moved? Or you press a button and it's like, didn't work. And now you have to like turn everything by a tiny margin.
So a little bit. I look at my camera detector and where there was something the day before, I'm reading no signal. And I think there's like probably about 40 knobs I can turn.
Oh my gosh.
No one of those on their own will fix it. So you have to be really methodical or it will take you forever.
So a great April Fool's prank for you would be...
Great. Great?
I think that's how you get thrown off the roof of the physics building.
Yeah. You never mess with an optical table.
Yeah, don't do that. Yeah. Make yourself as heavy an optical table so they can't do that. That's what you gotta do.
Some people super glue their mounts so that you don't have the option to ever unscrew anything.
Whoa, that's commitment.
It also ruins your optical table.
Yeah.
Not the table, the actual component.
Oh, okay. That's not too bad.
Oh yeah, our supervisor would have a field day with us if glue got anywhere near the table.
Laser weld to the table.
That would be bad.
How much is an optical table? Let's make prices right. Let me guess. Let's each guess. Wait, Tessa knows. Okay, me and Vinny will guess. Vinny will have a better guess, obviously. Okay, I'm looking in your eyes. I'm trying to sense
how much an optical table
the price. How stressed are you about buying an optical table?
STEM Price is Right.
$5,000.
Oh, it's way more than
more than that. It's a table.
No, these are they're like incredible bits of engineering. They're like hyper precise. They're huge.
I don't know how they drill the holes so well. Like they're so well spaced. They got to
be laser guided.
Laser cut. Someone else is in your very lab maybe doing this.
Well, we do have a cell that does laser cutting, but we have like the meh cell where it's kind of okay at welding, it's kind of okay at cutting, it's kind of okay at drilling. It does everything like
Sorry, laser.
Yeah. I know these are like tens of thousands of dollars.
Tens of thousands. Is that what you would say? Wow.
Easily.
Yeah, they're not cheap.
And then good luck getting it into your building too.
It's like moving a grand piano.
Oh my gosh.
Yeah.
We actually hire piano movers.
That's it. Yeah, they don't mess around with these things. Now Tessa, like, do you have to worry about have you gotten hurt by any of these lasers? Like, are you worried about getting a little zip?
So we have to be really careful. No one's ever been killed by a laser, believe it or
not. That's a good bar.
Interesting.
Directly. A lot of people have been killed by the electricity supplies. So we actually have to be really careful with electrical safety, because the power that if you have a perfect laser and you're able to convert all of your electrical energy to optical energy, then you're looking at probably 10 or 20 times the amount of power your wall outlet looks at. But our lasers aren't perfect. If we're getting 50% efficiency, we're really happy. So you're looking at huge voltages. You also have to worry about blinding yourself. So we have fancy glasses. So we always wear those. And you'll notice if you ever get to go into a laser lab, anytime anyone bends over, you'll see them put their hand up next to their eye, near the table, to block their eye off, just in case.
Mm-hmm.
So do the glasses wrap around?
They're like cool Oakleys from the future.
Or the past.
Or the past, yeah.
The 90s Oakleys. What are the 3 coolest things that lasers can do, or the 3 coolest lasers you know of? Do you have some?
So I really like sensor stuff. The laser welding is obviously cool because I get to melt stuff with light, which is always neat. My inner ant killer with the magnifying glass is very happy. But I really like the applications where we're actually able to improve the safety of the world in a really easy to market way, where companies will implement those solutions. So that was a long answer. So top 1, I love proximity sensors because I'd love to own a self-driving car one day. Those are often laser based. 2, of course, I love the laser system I work on. And a 3rd one. You know what? Laser pointers. Laser pointers are a big deal. Anyone who's had to be in a university lecture theater can appreciate a good laser pointer.
And I suppose since those seem like a low risk, they're like a real weak laser.
They're very low power laser.
That's why we give them in the hands of plebes like myself, who don't even know what lasers are.
That's right.
I shouldn't be handling
do not point them at people's eyes. Yeah.
That's a class 1 laser.
Yeah.
Okay.
Which means that you can stare at it until you blink and you won't hurt yourself. But if you feel the need to blink and resist it, then you'll hurt yourself.
Ooh. And so what class are the lasers you work on then?
I work on 3B is the type that my measurement laser is. So it's about 100 times as powerful as a laser pointer. And then the big laser is probably 1,000 to 10,000 times more powerful than a laser pointer.
What class is that?
4, class 4.
Oh. And what do we use those for? What are
welding.
Those? Oh,
welding. Melting stuff. The defense industry uses them for some stuff.
Destroying Death Stars.
Yeah,
Of
blowing up
course.
the Death Star. And the Death Star itself is probably class 5.
They made a new class.
Yeah.
Right.
Planet destroying.
Whoa.
Yeah.
So how does a proximity sensor work then? Like if anything disrupts, you can sense if it disrupts it? No, because it's just how close it is. So yeah, how does that work?
So there's a whole bunch of different ways to do it, but most of them are based on the speed of light. If you know what time the light left and you know what time the light came back, then you know how far it traveled. So that's one option. That's really good for long distances. They also do something called laser triangulation, where you like bounce a laser off of something, and as soon as it hits a mirror on the other side, then you know that you've hit a certain depth or a certain distance. But there's lots of ways they do it.
The new iPhones actually use LiDAR.
Yeah, LiDAR's huge.
And so that's like if you understand radar, where like a little radio beep goes out and then you pick up the echo off of it, you can do that with lasers that you can't really see. So it's not like a big red grid goes over everything like in the movies, but it's like an invisible version of that, where the laser light comes out of your phone and it puts a grid over stuff, and your phone the camera can pick up where those laser went, and it can reconstruct the distance from everything around the phone.
For what purpose?
For 3D like applications, like you can pass your phone around a room and then it'll recreate it in 3 dimensions.
Oh, like a panorama picture?
No, like a 3D model. Like it'll render a 3D because it can tell how far everything is. It won't be able to tell colors, but it can tell distances.
Interesting.
Yeah.
So is LiDAR like a type of laser? It's an application.
It's an application of a laser, like radar, but light radar. LiDAR. That's the short version of it.
It's not great. It's not a great name.
Well, what would you call it?
I don't know.
I want to hear what you'd call
LiDAR sounds like an insult.
it. You LiDAR.
Doesn't roll off the tongue. So you mentioned you were into robotics in high school, Tessa. Is that sort of where you would say your passion for science began, or can we go back even earlier in little Tessa's life?
Yeah, so I was not cool in school.
You're in good company.
I'm cool now. Or at least I tell myself I am. No, I always liked building stuff. Like I was always jealous of the boys who got the Hot Wheels track, because that looked like way more fun than like dressing up a Barbie. My grandpa actually, when I was 2, said I was going to be an engineer, and my parents rolled their eyes. So he gave me my iron ring last year. So that was very sweet.
Oh, that's adorable.
That's beautiful.
Good job, Grandpa.
Right. But yeah, I ended up kind of doing a little bit of everything with the sciencey stuff. I liked doing rockets in the summer, because who doesn't love blowing stuff up? And then I got into robotics pretty heavily in grade 10. And that's where I really got excited about what I could do in the future by going to school.
Tessa, you're definitely cool now. If nothing else, you work with lasers, right?
Yeah,
that's a mic drop right there.
Yeah.
For cool.
My nephew thinks that I might be a Jedi, so that's okay.
Yeah. I think you might be a Jedi.
Yeah, I think we have incontrovertible evidence that you are. Lasers.
Yeah, so where do you see yourself like kind of progressing with all this stuff? Like, is this like a field you really want to continue in, or academics, or more lab stuff?
So I actually, funny enough, I went to a talk earlier this week about academics transitioning to industry. And they were talking about all the things academics struggle with. And one of the biggest things is that academics want to 100% understand something and 100% get it perfect. And that's when I realized I really don't belong in academia, because I'm really happy with a good enough solution. So that was kind of something I realized. So I really like project management. I'm a bit of a control freak, and I really like to know what's going on in a whole bunch of different places at the same time, and then figure out how we can solve a lot of problems at once. Whereas in academia, you're kind of solving one problem at once forever, which just didn't appeal to me as much.
Yeah.
It does feel like a long time to spend on one question.
Oh my gosh, yes. You get so sick of that topic by the end.
You see the third-year PhD students, and they just look a little sad.
Yeah.
And exhausted.
Yeah. So are you planning on doing a PhD as well, Tessa, or are you hoping to go into industry after your master's?
I'm planning on going right into industry. I did a COVID master's, so I started
Right.
last May, because
Oh,
there's been
wow.
nothing else to do. I'm actually
Okay.
graduating 4 months early, so I'll
Nice.
be wrapping up in
Congrats.
January.
Well, that's great because we've talked to some people who, were inhibited from going into the lab as much and are going to take much longer. That's awesome that you were able to go to the lab during COVID.
Queens has done a really good job of making sure researchers can get in, and it makes a
Mm-hmm.
big difference because we're directly related to the manufacturing industry.
Hmm.
Aha. Yeah, I
Yeah.
guess if you're studying frog behavior, it's harder to get to sell yourself as an essential.
So Queens doesn't actually do a ton of manufacturing work, but we have a company that was actually founded out of our lab by a PhD student. So we are working on kind of, I would say tangentially, what they're working on commercially. But the advantage of being in academia is we can do things that won't make money tomorrow. We can try
Yeah.
things that we're not sure if they're going to work, which is kind of the exciting part.
Yeah, I mean, a lot of academia, especially in the industrial applications fields, is about looking at things that don't have a direct application immediately, but often have ways to get applied and sold and improve systems all over the place. So it's a really good fit. There's a lot of overlap between academics and industry.
And you have more opportunities to fail, which is like a good opportunity to learn.
Yeah.
So are you hoping to, in industry, work with lasers, specifically the type you're working on now, lasers in general, or just any sort of building type thing in industry?
I want to do sensor systems, particularly stuff that's on safety critical components. I was also the safety captain on the robotics team for 3 years running,
Nice.
so
Yeah.
that made me extra cool.
Hmm.
Um, but I like doing stuff where I can kind of see what the impact is. So I worked for a company between first and second year that was doing pipeline inspections. And it's technology like that that gets me excited, where we're kind of avoiding catastrophe by spending a little money now.
Hmm. Yeah, I mean, what's it? An ounce of prevention is better than a pound
Pound?
of cure. That's a
I think
weird
that's the
expression.
one, yeah.
It's so weird. I guess I'm as a metric person. That's just extra weird.
Yeah.
It's like a gram of prevention prevents a kilogram of cure. Meh. It doesn't translate.
Yeah, why ounces to pounds?
Well, I mean, that was probably the standard back then.
Damn it, imperial system.
Imperial system.
Oh,
It's
anytime
bad.
I have to deal with a machinist and I bring them a drawing in metric, they're like, use imperial. I'm like, yeah, you join the rest of the world.
Right? I mean, it just seems
Yeah.
better. It just is a system. No.
Oh yeah, quarter. Yeah, an eighth of an inch or 5/16 of an inch.
Oy
Get out of
vey.
here. Why? Who came up with that?
So
But Vinny, you're in optics. You've done that before.
Oh,
You know that what a
absolutely.
pain that is.
I do know.
25 millimeters does not equal 1 inch.
Nope.
Not on an optical table.
Not at all. It's brutal.
So do you get to build a lot of the things for your table then? Like do you design them and other people make them, or you go to Home Depot and
No, not Home Depot. I have an extremely expensive optical Lego supplier, effectively.
Whoa, cool.
Where you buy different components and you assemble them, and there's different ways to do stuff. I actually last week got to make some of my own optics. I
Nice.
went into a nano fabrication facility,
Whoa.
which was really cool. So you have to get gowned up because dirt is the enemy. And all the light is orange, which is kind of funky too, because
Whoa.
the chemicals we work with in there are exposed by ultraviolet light. So I actually got to go in and do that last week, which is something in industry they would never send you to do as an engineer. So that was very cool.
That is very cool.
Do you ever worry? Okay, conspiracy theorist time.
All right, we love
If
this.
it's a nano lab and everything's
Yes.
teeny tiny, could they just be pretending they're doing stuff all day? Just putting it out there.
Who?
Because everything is
the,
teeny.
The engineers or
Yes,
the nano
they're like,
bots?
yeah, no, they're tiny. You
And you're
just
worried
can't
about the
see
tiny
them.
things that are up to no good.
No, I'm worried about the scientist line, like an
They're
emperor's
making
new clothes
they're
scenario.
making naughty nano things.
No, not non-nano. There's nothing there.
Oh, it's just they're just pretending.
Yes, they're
just
pretending because they're so small. Thoughts, Tessa? Is this a conspiracy?
I haven't heard that one before.
I'll get on the internet.
Maybe.
It's not
Probably not with how expensive lab time is.
Yeah.
I think someone would sue someone else if they found out about it.
Good luck finding the nano things. They're tiny.
So
I thought of everything.
The most stressful thing about those rooms is making sure you don't drop anything because it gets sucked into the filtration systems. So we use this tape to tape stuff down, but it has this super annoying clear backing. And you put it down on the table and then it's gone. And you have to find it. You can't just like be like, oh, I guess it's gone, it's fine. No, like you need to scour the lab floor until you find that 1 millimeter by like 4 millimeter piece of tape that you lost track of.
And it's because there's like suction going on in the room?
Yeah, these rooms are kept under negative pressure so that the dust can't stay in there. It's constantly the air wants to go out.
Wow. So do you like your ears pop when you walk in? That's my main concern.
Some apparently, not in our clean room, fortunately. That would be upsetting. But no, things will just, you have to make sure you put it right in the plastic baggie, because if you don't, you are going to have a bad 2 hours.
Yeah.
Oh, man.
Yeah, precision manufacturing is wild. It's very precise.
It's a good place for a perfectionist.
Yeah, I guess so. Yeah. Yeah. If someone is really good with details.
If you're sloppy, I'm a sloppy scientist. That's why I'm in biology.
Yeah, macro
That's
scale.
where you're covered in mud.
Yeah, scuba diving.
You know, if you lose a frog, there's more. You don't have to find that frog.
You can find a new one.
Yeah, it's fine. No one
Unless
cares.
you're looking for like, what are they called? Endlings?
Ents? Oh,
endlings, the last of a species.
Oh. I've never heard that term before.
Yeah, it's the last of its kind is an endling, and it's the only one left.
It sounds like it's from a Tolkien novel. Endling.
The endlings are here. I guess there would only be one, though.
So, Tessa, looking sort of to the future of lasers, is there sort of a new domain that lasers are being used for? Ooh. Like, what's like the frontier of lasers that you know of?
Cool kids of lasers.
Well, we know Tessa is, but who's next?
Yeah.
So in terms of manufacturing with lasers, I would say the additive people were the cool kids, but because of electric vehicles, the laser welders were making a comeback.
Nice.
Just in general, I would say laser telecom is really interesting. They're doing some really cool encryption stuff that's like quantum encryption using lasers.
Whoa.
Took a course on that during undergrad. Don't totally understand it, but someone is doing it.
Mm-hmm.
Keeping it real. It happens.
What happens?
Well, we all have courses where we're like, I don't know that I got that one.
Sure. Yeah.
It's good to talk about.
Yeah, there's definitely classes that you take. You're like, well, I needed that for my degree.
Yeah, I had so I'm an ecologist. I had a course on like some chemical communication between organisms and ecology. It was very cool, but I clearly understood nothing of it.
In third year, I hit the point where I was taking a math course. I was like, I don't need to know anything else about math. Like, I hit that point. Yeah. In second year, I was still excited about math. I was like, I love math. Math is cool. And then third year hit, and I was like, oh, math is philosophy now.
Yeah, there is that time where there's more letters than numbers.
Yeah, and infinite Hilbert theoretical spaces are great. So yeah, Tessa, tell us about your dog and teaching them new tricks. That fascinated me. What kind of, like, does your dog like love learning tricks?
Do you use lasers with your dog?
So funny thing, you're not supposed to use lasers with dogs because it gives them a psychological complex. Because they can never catch the laser. So you're not supposed to do that, I learned. So I keep my research separate from my dog. Mm-hmm. He is a 2-year-old standard poodle. His name is Frodo.
Nice.
Hey, we just talked about
Lord of the Rings, yeah.
Standard poodles are really smart, so they need to be kept very occupied or they will ruin your life. So in my free time, I actually compete with him in agility, and we also do obedience together. So those are my outside of physics hobbies.
And so is this a PSA? Should people not be using lasers with their cats as well? Because I always think of cats.
So apparently cats don't have as much of a complex about it, but I guess that's fascinating.
Different kinds of hunters?
Maybe they're like more okay with failure, whereas the dog goes back to its kennel and like beats itself up about it.
Oh wow,
that is devastating. Poor doggies.
Yeah, don't do that to your dogs.
So you compete. How do you compete for? Are you doing like American Ninja Warrior obstacle courses with your dog?
There's jumps, there's tunnels, there's A-frames, there are weave poles.
Amazing.
Wow.
So this is like that Westminster dog show kind of stuff.
Yeah, kind of. He barks at me when I get the course wrong.
That's amazing.
Wow, he's whipping you into shape.
Yeah.
Yeah.
Maybe you can both be project managers.
There we go.
He's laser precise as well. And you also mentioned you're into sourdough. Now a lot of people have taken up sourdough because of the pandemic. Does your interest in bread predate the pandemic, or is this a new hobby as well?
So I worked at a bakery in high school.
Cool.
Where we made sourdough from scratch every morning. So we would mix like 50 kilograms of sourdough starter every single night. I actually kind of thought I was into chemistry at that point because I thought it was neat. And then I realized the only part of chemistry I liked was physics. So that was the end of that. But yeah, I've been doing sourdough for a while, and it's kind of fun because you can do lots of different stuff with it.
Yeah. Do you use anything that, like any of your physics knowledge to perfect your bread?
I would say not necessarily the physics, but the record keeping. Like record keeping is such a big part of science. So I make sure like I know exactly how much it was fed, whether it got white or whole wheat, how long it was at room temperature, if it's hot out, humidity levels, and then I can like compare how the bread came out.
So what are some tips you've got? You certainly must have some good advice.
So one is definitely have a container that's way bigger than you think you need, or you will have to clean your fridge.
Right. Now, did you have to learn that lesson the hard way?
Obviously.
So I didn't.
Oh, okay.
I had someone else feed my sourdough while I was gone, and Bubbles, my starter, was not so happy when I got back. Whole wheat flour is critical. Doing like half whole wheat, half white is like seems to be the prime blend.
Is that for flavor or texture or both?
Seems like the starter is just happier that way.
Interesting.
I don't know anything about biology. I ran the other way as soon as I could because I didn't want to deal with goop or anything of the sort.
Yeah, biology is very goopy.
Yeah, you get pretty immunized to that.
I would say it's the goopiest science. More than chemistry.
It's definitely the gross, probably the stinkiest. I don't know.
There's some chemical engineers that would probably argue with that.
I mean, as an ecologist, I've dealt with a lot of dead, rotting poop, guts.
Yeah, that's real goopy.
Yeah,
I like physics.
Goopy.
Yeah. Optical tables, they're very clean.
I would have loved some
spotless.
negative pressure rooms in those dissections, let me tell you. Suck out that formaldehyde smell, please.
No,
well, Tessa, I think we're
at the end here.
Oh my gosh, that flew by.
Fast.
Thank you so much for joining us, Tessa. Best of luck with your laser. Stay safe with your cool guy glasses.
Yep.
Thank you.
And good luck finishing up your master's.
Yeah, thanks so much for joining us.
Thanks for having me.
Wow. Lasers.
Lasers
are so cool.
They can do a lot.
So you seem to really resonate. You are like living your best life when Tessa was talking about an optics table. Now, did you use an optics table?
Yeah, I used an optics table. I had an internship back when Nortel was a company. And they used lasers. Well, I mean, fiber optic communication is it's like a wire made out of glass tubes. And one end you shoot a laser and the light comes out the other end. And so they can only go a certain distance. So you have to be able to put them together and whatnot. So we used lasers in fiber optic communications all the time. And so I worked on an optical switch, which means, so like, how like binary code is transmitted 1 0 1 0. So laser on 1, laser off 0. And basically you could shoot a laser down 2 paths of different semiconductor material. And then if you applied a voltage to one path, when it remerged, it would be offset by wavelength offset by 180 degrees, so that when the peak on one end was a trough on the other, and it would come out canceling each other out. And so these are called Mach-Zehnder interferometers.
Why would you remember that?
It's a great name.
That's amazing.
And so you basically send light down two paths, and you can leave them alone, and they'll remerge, and the laser will stay on. But if you apply a voltage to one of the paths, it will flip it upside down and cancel out at the other end. So it's an easy way to just apply a voltage to turn a light on and off. And you can do it very quickly, which was an important task. So I did research on that.
I mean, as someone who still loves Lego, I feel like that's your best life. Right?
Oh yeah, optical tables are awesome.
Yeah, you could just build optics tables for other people.
Yeah, it's almost like those marble mazes that you can build. Like when you drop a marble at the top and it goes down and it goes through a windmill and down some stairs. But with a laser, it's light that's doing that.
That reminds me, we had a competition in my school when I was like in grade 4. I can remember because who won was in grade 6, where you had to build like a Rube Goldberg machine, basically. And I always prized myself as being the top student at the school. So I had a lot of pressure on myself to do this, but I didn't have books on marble mazes or parents who had any idea what was happening. And so I had like this idea in mind of what I would do. And I was obsessed with this idea that at one point you'd knock over with a marble baking soda into vinegar and it would inflate a balloon that would like rise up and push something. But there was no way to generate enough gas or have enough pressure to force that gas.
The balloon.
It never worked. I was devastated.
Well, it's not too late. We can still try it out.
Yeah, we'll do that. Now that we're mostly done the pandemic, let's build a marble Rube Goldberg machine. We're going to make that balloon work.
Well, thanks for joining us, everybody, for another episode of Learn Real Good.
How do people find us on socials, Vinny?
Well, that's a great question. They can find us on Twitter, Facebook, or Instagram at LRGPod. That's LRGPod.
Are you selling something?
For all your Learn Real Good podcast needs.
And for any grad students out there in the STEM field interested in being a guest.
If you want to contact us, send us an email at learnrealgoodpodcast@gmail.com.
Wow. I'm going to buy that email address.
We already have it.
I was talking about the fact that you sound like you're selling something, you're doing a good job.
$19.99.
It was a great year.
That's the price.
Yeah, right. Great Prince song.
We'll edit that out.
No, it's perfect. Thank you again to our wonderful guest, Tessa. Thanks for listening, folks. See you next time.
Take care.